Hey YouTube, JP Dillon. This is going to be part 3 of the Sanusi resurrection, the submerged 5500. Now we've got the case all shored up so that we'll have something sturdy to put it back into. As you may have recalled from the initial test video, we determined that there was a problem in the right channel of the amplifier. The radio didn't work worth a crap, a whole bunch of kind of remedial dirty switches and controls. So today we're going to take a look at the amplifiers. Now, on the 5500, the control driver boards for the amplifiers are underneath this plate. And then you've got a left and you've got a right output stage. Now, I can already tell somebody's worked on this, because if we look here, if the camera will focus, there we go, we got EGC 284 there. This is a single-ended design, so it's 2 NPNs. And EGC 284 there. So at some point the outputs failed and somebody replaced the output transistors. Now, I'm not really a fan of ECG and NTE devices. They're close. I guess they'll work in the basic sense, but they're not my favorite thing to use. I much prefer using the actual device, or like an MJ device, a non-semi device. Much better. I'm just going to pull the shield off here real quick. And we'll just pull a card out and see if there's any evidence that somebody's been messing with it. In order to do that, there's a screw at the back there. And before you can take a card out, you have to remove 2 screws. There's one down there at the bottom, and there's the other one down there. There seems to be a large concentration of fluid here, pursuant to it being underwater. So we got to be on the lookout for parts that have been eaten, foil traces that have been destroyed. And although this did work and pass signal, I don't want to say we can just toss it back in the box and go yet. As you may have recalled, the right channel would draw lots of current when you cranked it up. Okay, so we're essentially looking at a completely stock board. And obviously, there's probably a good chance that all these capacitors are bad. You can definitely see that one there on the right is got corrosion around the top, probably because it vented. So that will need to be changed out. This one does not appear to have 2SC2240s. It uses a 2SC871, which was the upgraded part. Older designs use a 2SC458, which was then replaced by a 2SC1740 and later a 2SC2240, and then later a 2SC2547. So, these original Hitachi devices, we'll need to check those. With a direct coupled design, when an amplifier fails, if the output's short collector emitter, meaning there's no feedback through the driver stage, you can usually just replace the output transistors and bias transistor and it's fine. However, if it shorts collector base, then immediately you've got reverse current flowing through the driver stage, which are those TO66 type things right there, and those can get hurt. And then if they short, again, that will go back up to the Class A device up here. So depending on how the amplifier fails, you'll want to test everything. Now, since we don't know what the real history is on this and why they replaced the outputs, I'm going to test those transistors anyways and see if there's any leakage between the collector and the emitter, which is usually indicative of the device being injured. So we're just going to start with one driver card so I can show you the principles of testing this. And then we'll pretty much do the other one off camera. And then when we get the amplifier sorted through, we'll power it back up. Now, the original devices in the 5500 were either 2SC1111 or a 2SD218, depending on what it was. I'm kind of curious about that. Let's look at the NTE 284 real quick. Okay, so here's the data sheet. Now, if it was a 2SD218, it would have been about a 180 volt, I believe it's a 15 amp device, 120 watt at about 6 megahertz. The 284 is 180 volt, 16 amp, 6 megahertz. So this would be a decent substitute. That's an okay thing. We'll probably just leave them in. By the way, ECG and NTE devices are the same. The NTE Corporation superseded the ECG number prefix and pretty much just left everything the same. Sorry for the shakes here. But really, when you're substituting parts, it's not just voltage, current, and wattage dissipation that's important. It's capacitance of the collector and also the bandwidth. You want to try to keep the bandwidth the same. If you don't, then you'll change the phase shift in the feedback loop of the amplifier, which can cause an oscillation and blow up the set. So since we know that those transistors are adequate for the design that they're currently in, we'll leave them there. Okay, so what you're going to need is a ESR meter to check your capacitors, a DMM if you've got it for basic function, but really the best thing to have is an old voltometer like this RCA voltomist. This is a WB519A, as in Whiskey Victor, and the cool thing about this is that it's got a 22 volt battery in it. So on the R times 10K, it's putting about 20 volts through the device, which will really help reveal leakage. Now obviously if you've got some really nice Sencore transistor and SCR tester, that will work, but most people don't have that. You can find these on eBay. Make sure that you tell the seller to pack it really well so the meter movement doesn't get damaged. So what we're going to do is I'm going to take a pen, and just for the ease of doing it, we're just going to circle all of the capacitors that are here on the board so that I know where to stick the probes of the capacitor checker. I'm probably going to end up having to replace most of these because they're old and you can't really trust caps that are 40 years old. I'm not going to recap the whole thing. Sorry guys. Don't want to do that. It's a big use of time, and I'd rather troubleshoot what's bad. Now, if you're looking at this board here to the left, you're going to see a darkened area, which is this guy over here. Why is it darkened? Probably because there is a giant resistor there on the other side. That's a 6.8K. And what that appears to feed is the that's the base of one of the driver transistors. Now I can't find an identical resistor on the others for the other channel. This is the NPN side, or a PNP side. That's the NPN side, unless I'm not seeing it. But in any case, that resistor got hot, so we may want to check that. So let me get the camera strapped up, and then we'll check all the caps and see which one needs to be replaced. So far, so good. That one tests about a 2 on the scale, which is about a 10 microfarad. Let's flip it over and see what it really is. It's a 3.3 microfarad, so that tests pretty good. And then the one next to it here, that tests pretty good. That tests like about a 20. That's a 4.7. So none of them are open. However, the fact that a lot of these test way higher than they should be suggests that they've gone up in value. Now, what happens when a capacitor nears the end of its lifetime? The electrolyte dries up, and that causes the aluminum foil wrapped around the dielectric to shrink. And as it shrinks, the foil gets closer together, and that increases the capacitance. But at the same time, it lowers the voltage handling capability, which is why when capacitors get really old and tired, they will usually short. Sometimes they'll open, but they'll usually short. So, given the age of this machine, and the fact that this one here has that kind of corrosive, frosty appearance up top, even though these all check okay, I don't really trust leaving them in there. So I'll probably just pull them out. Now, the next thing I want to do, since the output transistors were replaced, is I want to check the drivers, because I don't know if the original devices shorted collector base or not. So we need to find out whether these Class AB drivers here got hurt or not. And that's usually revealed by leakage between the collector-emitter junctions, which I'm going to show you how to test in just a moment. But the first thing we need to do is get them out of the circuit. So we're going to unsolder them, and then we'll pull out our VOM, and we'll put a current through them, and we'll check them. So let me unsolder them, and we'll get to that. Okay, so now I've got them unsoldered here. And we just want to take and push the leads a little bit over so we don't have any contact with the circuit. Otherwise, the current that the meter gives will energize other parts of this board, and you'll get a false reading. Now, a DMM will test for junction, and we'll check it to see if it's nominally alive, but it's not enough current to check for leakage. So what I'm going to do is we're going to take our VOM, we're going to put it on R times 10K, and we're going to measure between the collector and emitter. Now, if the transistor is good, we should get a little bit of deflection in one polarity, but not the other. So I'm going to go from collector to emitter here, and we get no deflection. And collector to emitter here, we get deflection. So this is okay. And then go back to R times 1 and just do a basic junction test. This is our PNP, so we've got between base and collector as a junction, and between base and emitter as a junction, so we're good there. So this PNP side is perfectly fine. Go back to R times 10K and do the same test on the NPN. And in one direction we get deflection, and in the other direction, there we go. See if I can zoom in on that. So you can see here that we're close to zero. In one direction, I get deflection. That's normal. However, in the opposite polarity, I was getting a little bit of meter deflection here, which I'm not now. Yeah, good continuity. Oh, there we go. See how the meter deflects a little bit? That's leakage. Deflection, no deflection. Deflection, no deflection. That device is defective. So we need to replace that. Leaky drivers lead to excess bias, overcurrent of the output transistors, and ultimately failure of the new devices. So probably one of the transistors shorted collector base, and they didn't pull this device. This may be for the right channel, but I don't know. Out of curiosity, I'm going to pull the other board, and we're going to check the other board next. Alright, so here's the other driver board. We're going to check these devices too, just in case. So on the PNP side, oh wow, we got quite a bit of deflection there. So that's trash. That just failed right off the bat, didn't it? Let's make sure that we're not connected to anything here. Looks like that post is separated there. Let's do a quick resistance test and make sure that it's not. Yep, it's separated. So that device is defective. That's got heavy leakage in it. And let's do the NPN side here. You got deflection one way, and a little bit of deflection the other, a little bit more than the other. So this amplifier went down really hard. Sorry, it's not focused there. Let's check that again just so you can see it. Again, in one direction, got a little bit of deflection, The other direction, we got normal deflection. But this PNP on this driver is in terrible shape. So the amplifier had a severe failure, and the guy just kind of, well, he was lazy about it. He didn't want to pull the cards out and replace the components. Oh, yeah, just replace the aperture. It's the easiest thing to get to. See that a lot. So now, of course, the question is, you're not going to be able to get those brand new TO66 transistors anymore. So what do? Well, you have to replace it with something of equivalency. So the next thing you want to do is we want to look up the characteristics of a 2SC680 and its counterpart, the 2SA566. Now you can either do that online, which is what most people do, or if you're lucky enough to have it, you can get the Japanese transistor manual, which I'm going to show you in just a second. So this is a well-used copy of the 1982 Japanese transistor manual, and it lists all the important characteristics. So what we'll do first is look up the 2SA566. And it's all in numerical order. Here we go. Okay, so the 2SA566. Let me move the camera so I can show you how to read this. Since most people can't read Japanese, obviously this is the number. This was the type, application, type of transistor it is, whether it's a silicon epitaxial, Darlington, etc. And then you have your VBO, EBO, your current, your power dissipation, your maximum operating temperature, and then you have various current conditions pursuant to transistor theory. I don't even remember what all of these are. And then you'll have ones here, which is your gains if published, beta, junction resistance, your bandwidth, which is really important. So anyway, looking at the 2SA566, this will focus again, come on. Looks like 100 volt, 700 milliampere, 10 watt, running at 100 megahertz. Really? 100 megahertz for that sucker? Let's take a look at that. Wow. Yeah, 100 megahertz. Wow, that's a pretty quick device. Let's see if it lists the capacitance. There, 25 picofarads is the capacitance. That's going to be a hard one to match. And then I'm going to assume that the 2SC680 is very similar. There we go. Now that's weird. Now the 2SC680, although it's in the same package and it's listed as a complement, it's a 200 volt, 2 amp, 12.5 watt, running at 20 megahertz. And it is 75 picofarads. How weird. So it's not an exact perfect electrical pair. Now, this is going to be tricky because we have such different values. We've got one with 75 picofarads, and the other one was, I believe, what, 20-something? 566. I'm in 2SB. That's why it looks funny. Yeah, all this is important. Yeah, that was 25 picofarads. Maybe they're trying to have a combined collector capacitance of 100 picofarads. Who knows? So, the next part of the video, we're going to be searching for things that are appropriate to replace this with. But we have troubleshot the amp and found out that what's really wrong is it blew out and the guy wasn't thorough enough. So the next part is going to be us investigating good replacement parts for this device. Alright, so I've been searching quite a while on these things, seeing if I can find something equivalent. But really the difference we're running into is the bandwidth between the two. As I looked up in the datasheet before, the specs for the 566 run it out to 100 megahertz, and has 25 picofarads collector capacitance. The other is the 2SC680, which is 20 megahertz at 75 picofarads. Now, as you can see, I've looked at these MJE devices, which I've used for older sets in the past, which run at 30 megahertz. There's no publication as to what the internal capacitance is, so that's kind of a drawback. But as you can see, that's what I've come up with so far. And I've looked at other devices in it, like a TO220 package, and really, if I go out to about 100 megahertz, then I'm losing power dissipation capability, or I'm losing voltage capability slightly. So I'm not sure why they would have had such different bandwidths. So what I'm going to do, also, just as a side note, people have been asking me via email, it's like, well, why don't you just cross-reference it with an NTE part? Okay, so I go to NTE's catalog and punch in 2SA 566, and they come up with an NTE 284, or not a 284, 281. But the 281's only at 3 megahertz, and it's got 100 picofarads, so that's too fast. Or it's too much capacitance and it's too slow. And technically, it's just probably not going to work out very well. These designs have a lot of leeway, and you can kind of mess with them a little bit, so I think that's what I'm going to do. What I may end up doing, I think I'm just going to mount these MJ things and test it out and see if we have oscillation and see if it's load picky or anything weird like that, and then we can kind of tweak the circuit. But I think really in this package style for this duty, this is probably the best thing that I've got on hand. And this set really isn't worth my time to go spending hours and hours of research figuring out what perfect match I'm going to find for this thing. I really just want to make it work and reliable and not go nuts on it. Obviously, I can pay about $15 to $16 a piece if I want new old stock devices, but then you got to question, are they okay? So I'm going to mount these in place of the TO66s, and it's really not hard to do. As soon as I get these cleared off the board, I'll show you how to do that. So we can see, looking at the two, that they're very different looking in appearance. And the case on this is the collector, as is this, although it has that third lead that's protruding out of the bottom. So what do you do about that? Well, what I will do is I will just cut off the collector lead, since we're going to be mounting it to the heatsink here. But essentially, once you cut off the lead, you're just going to orient it so that the pinout is correct. And obviously you want to make sure that you're mounting the collector onto the portion of the board where the collector is supposed to go, here. And then most of the time, let's just lay this down to make sure. Most of the time you will not have to replace the mica insulator. There will be enough space. And if we lay this down on here, we find out, it's a close, there's enough space. None of the metal's getting close to the heatsink, so I think we're good there. So I'm going to mount it up and then show you, because that makes it a whole hell of a lot easier than trying to fumble with the camera and mounting it and all that sort of thing. So once you see it, you'll understand. Okay, so there it is, all mounted up. And what I've done is I've just bent the leads over so that they go through the appropriate holes in the circuit board and secured it. And I know it doesn't look like it, but if we zoom in, the header is not contacting the metal. We're still on the insulator there, so we're still good. So that's how you mount a TO220 in place of a TO66. And we'll do the other one here. And I may have to, well, no, I've got enough lead stretch. I can probably get it on the header of the other side of the TO220, and then we'll solder these things up. And then we'll put it back in the amplifier, and we'll run the dim bulb test again and see if this channel is capable of running. And if so, then we'll just do the other board over there, and that will be our amplifier repair. And then, of course, I have to replace all these capacitors, but that should get it running. So let's replace the other device. Alright, So there they are, all mounted up. I just reattached the bias driver right to the heatsink rather than the header of the transistor, which might actually give a more accurate reading. Got them all soldered up. So all we have to do now is pop it back in the machine, try it with a dim bulb tester and see if it wants to blow up or not. Alright, this is the moment I'm sure you've all been waiting for. Will it work? So we've got one of our driver cards in there, and we've got a load hooked up, and we've got our dim bulb tester there. And so we're going to flip the switch and see what happens. Obviously, that was the left channel, because I saw the left channel bobble there. Okay, so we've got a signal. We still have our crummy volume control and such, but... Alright, so let's focus on the left side. Yeah, it's going to be crummy because we still have all of those funky switches and stuff, so it just kind of is what it is. We're cranking it up, though. There's no oscillation. So that's about maybe 5 watts. Cool. Alright, let's take it off the limiter. It doesn't want to make the bulb super bright. It doesn't want to go nuts. So let's take it off the limiter. Alright, without the limiter, let's turn it on. Wow, it's a fair amount of power. Ah, see? We got a little bit of oscillation there on the positive half cycle. That's kind of what I was fearful of. But we are getting symmetrical clipping, which is good. Okay. So we're getting a little bit of oscillation there. Let's see if what happens when we go up in frequency. You can hear it singing in the transistors. You can better see it. It's a fairly high frequency oscillation there. And it's on the positive half cycle. But it's only after you get to clipping. And you've got one on the negative half cycle there that's a little sheety. Certainly doesn't like super high frequency. It starts to roll off after 30K, that's whatever. So if we go out to 20K, yeah, then we get a major oscillation. So those may not be the best choice. Okay, but that does tell us that it is capable of running without blowing up with drivers in it. So I can either try adding some capacitance between the base and collector of the NPN driver and see what happens. And then we'll plug it back in again. Nominally it works though, so I'm going to see if I can snub that oscillation and then we'll try again. Alright, so as you saw, this setup did run, but we do have oscillation, particularly in the positive half cycle. I tried adding some snubber capacitors in the driver stage to kind of smooth it out, but it really only helps marginally. It's not hi-fi. So I'm on the hunt for something that meets our specifications. And once I can do that and find a solution that actually works, we'll get this running. I may have some old stock parts, but we'll see but nominally I definitely need to locate at the very minimum, something like a 2SA 566. And for some reason it wants those different bandwidths. I don't know why they designed it that way. Maybe there were shortcomings of transistors available at the time. Maybe it was a production change. Don't know. But anyway, I will look around for some devices that work. We'll toy around with this a little bit more, and then if we can get it working, then we'll move on to the next part of the repair, which would be the radio. And then we'll, after the radio's fixed, assuming everything else goes well, then we'll clean up the faceplate. So I'm going to go look for some devices. Next video you'll see will likely be of me finding something that works. Stay tuned. Alright, so this is the kind of awesome I like to see. These I found going through a junk pile of stuff that I had in a box labeled Sanusi stuff. And I don't know if you can see that, but these are the actual Hitachi devices. I have no clue if they're good or not. We're going to test them. I probably scrap these off of another Sanusi at some point, but who cares? We're going to test them out and see if they're any good. So let's pull out our first NPN, and let's just do a basic test here. We got a junction there and a junction there. Do our R times 10. Ah, shit. That's leaky. Quite a bit leaky. Alright, so we're not using that one. Let's look at the other. Let's just do the leakage test real quick here. That one's even worse. Damn it. Well, it was a nice try. Let's look at our PNPs. These are the weirder ones, the harder ones to find. Got good one direction. That one doesn't have leakage, so that's good. That's our 2SA 566. And let's do our other one here. Good in one direction. Yeah, that one's leaky as shit. Damn it. Okay. Well, one of our original 2SA 566s was good. So I may pair it with this one, and then we'll still have to find the 2SC 680s. That's too bad. I'm just going to put these back in the bag and then mark them as leaky. I don't know why I keep them. They're a little leaky. Maybe they'll work for some ancient self-biasing type amplifier. Who knows? So we'll just mark these as leaky. Yeah, well, that's, you know, we got one part. We've got the other NPN we have is still good. So this and the other, or excuse me, this and the other PNP are still good. So I just need to find two SC 680s, or it may be, since the MJE 15030 is close to the correct bandwidth, that I can just put these PNPs in there and it'll work. We can try that cockamamie thing too. But it's good that I found this. This solves my PNP problem. Maybe I can look around some more and find more of these things. We'll see. Okay, so somebody suggested to me that a 2SA 968 would be a good substitute for the 2SA 566. And if we look at the datasheet here, let's zoom in here. I think I've got it. Yep, there's our place marker. 160 volt, 1.5 amp, 25 watt, and it's running at 100 megahertz with 30 picofarads, which is pretty damn close to what I was looking at previously, if I can find my little notepad. Because the original one was 25, so 30, that should work. Now the counterpart's the 2SC 2238, but it's also 100 megahertz rather than 20, and rather than 75 picofarads, it's 30 like this one is. So I'm going to try it with a 2SA 968, and then I'll use the MJE 15030 as its complement, and we'll see if we can get that to work. That may very well fix things, but I won't know until I try it. So let's pop this one in and then run the amplifier again and see what it does from there. Alright, so we got our 2SC 1986 for the NPN and the 2SC 968 for the PNP. Let's plug it in and see if it works. It's either going to blow up or it's not. So we're no limiter right now. We still got that totally bizarro oscillation. That's just really weird. It's trying. It's trying to oscillate. You know something? Let's look up what the original output transistors really were. Maybe there's some sort of negative interaction with the outputs that are in this thing. Or they aren't really what they say they are anymore. That's interesting. Let's go get the service literature on the 5500 and see what's really supposed to be inside. I gotta tell you, if you're looking for service literature, Hi-Fi Engine's a great place to start at. These people have been kind enough to pretty much update whenever they can with machines that they have. See, here we got your service manual here and an alternate scan. I'm not sure which one is better. I guess let's just try one and see what happens. Yeah, and we'll take a look and see what the outputs are really supposed to be. Alright, so it's TR 807 through 810. Let's see what those are in the parts list. Well, I've got to say, I've been through both copies of the service literature now, and I can't find what the output transistors are supposed to be. I can't find what they are. I've been through both copies. It lists the part numbers, but I don't see them here under other parts. I mean, I know what would have been common for that time. Maybe it listed on the power block here. Of course, that's regulated power supply. That's not what I'm looking for. Switch mode block, driver block, but they don't list it here on the parts list at all. It's like not there. They stop at 806. So it's everything but the finals, unless it's just on here and I'm not seeing it. Come on, scroll down. Yeah, I'm not seeing it here. We're going to have to do a little more research because both literatures that I can find don't show what the output transistors are supposed to be. Okay, well this version of the schematic pretty much confirms what I was thinking. This uses the Sanken 2SC 1116 as the outputs. That's a particularly fast device. We'll go look up the specs and I'll show you. See, if we look at the 2SC 1116, we see that it's 180 volt, 10 amp, 100 watt, running at 10 megahertz, and it's 165 picofarads of capacitance. So, although what they put in there was a 6 megahertz device, I'm pretty sure the NTE device isn't going to have 165 picofarads worth of collector capacitance, although we can check real quick. So yeah, looking at the data sheet, we come down here to the specs, we see that it's 300 picofarads. That's almost double what the 1116 is. So this is really our problem. This is why we're getting the oscillation. Because the collector capacitance is too high. Now we can look at the infamous MJ21194 and see if that's better, but I don't think On Semi publishes those specs, but let's take a look. So the 21194 really isn't going to work. It's only 4 megahertz and it's 500 picofarads. It's even higher than the original. So that's like, no, that's not going to work right either. So now you see what the problem is with a lot of these older solid state units, and that is the finding substitute parts that work in the circuit are very difficult. Now if I leave that amplifier as is, there's a very good chance that depending on the load that it will oscillate out of existence and it'll just blow up again, and all that work that we've done will be a complete waste of time. Now, I was under the impression that this generation of machine uses the slower devices like the 4 and 6 megahertz devices like the 2SD218, the 2SC111, etc. But this uses the 1116, which is a fast device with low collector capacitance. It's a 10 megahertz device with 160 picofarads, something like that. But anyway, it's vastly different than what we have. So I'm going to either need to find some units online that will probably be fairly pricey, or just say fuck it and move on. I can take a look at my spare stuff and see what's available, but I don't think I'm going to have anything like that. Those Sanken devices are very hard to get and they're very rare, and it used to be Wudang had them, which was over in Sweden, I think, or something like that, Wudang.net, I forget, but they don't appear to have any in stock as of this video. So let's take a quick look around, but I think this may be on hold for a while. Alright, so looking through inventory, I can't really find any replacement devices that are even close to what this requires. So this one's going to have to go on hold for a little bit until we can find the right output transistors. This guy just put whatever he had in there, which was what it cross-referenced to probably through the ECG catalog. In fact, I have the ECG catalog and we can probably look it up. Just out of curiosity, what it told him it was. 1116. Give me a second. Let's find this thing. Yeah, it says right in the catalog, the 2SC1116. You should replace with the NTE284. But it's just not the same thing, man. It's just really not. And the oscillation we're seeing is proof of that. And I really wish I had a set of 1116s to just pop in there and just to see if it would work, but I don't. So, unfortunately, like I said, this is going to have to go on hold for a while until we can come up with a solution to get replacement output transistors. Because I want to fix this right. I don't want to just slap whatever in there just so that it makes a signal and then have it blow up on me or somebody else, depending on who it sticks around with. But now you see what's really required to fix one of these things right. I mean, anybody can make it play again, but how is it to fix it right? Well, this is an example. So this is going to go on hold a bit until we find the right parts, and then we'll pop it in and see what happens. So anyway, thanks for watching so far. More updates on this project as it becomes available to get parts, and then we'll take off again and go from there. But thanks for watching.